What's up, guys? It's Misha. When electrical engineers designed filters and controllers, they used body plot to show the system's magnitude and phase as a function of the frequency. They take transfer function, enter it some software, and get a body plot to analyze and work with. And this body plot must make sense for engineers. I mean, to avoid garbage in, garbage out, they must expect some general shape of the body plot based on the transfer function they have. That's why at the university, students are learning how to sketch body plot by hand without any fancy software. These two textbooks that I used in some classes teach how to draw body plot. I'm not going to go over the steps, but today in me class, I will focus on one thing that is missing in both textbooks. Let's see what they say about picking in quadratic poles. The significant picking in the neighborhood of the corner frequency should be added to the straight line approximation if a high level of accuracy is desired. However, we will use a straight line approximation for the sake of simplicity. And the textbooks give some examples of picking for different damping ratios. Essentially, from these textbooks, we found that the picking exists, and that's it, no more information. Let's see what another textbook says. The transition through the breakpoint region has a large dependence on the damping ratio. A rough determination of this transition can be made by noting that the magnitude equals 1/2 zeta at corner frequency. And these textbooks also provide examples of picking at different damping ratios. Okay, from these textbooks we found that the magnitude of the peak can be roughly estimated as 1/2 zeta, where the zeta is a damping ratio. But there are some questions that are not answered. When can we use these estimations? Does the peak in the quadratic poles always exist? And finally, is it really difficult to find the exact peak location? Let's dive into the analysis and try to find the answers. Let's say we have a system with a transfer function that is a quadratic pole in its standard form, 1/g⍵/omega natural squared plus 2 zeta g⍵/omega natural plus 1. The asymptotic body plot of this transfer function is the following. It starts at 0 dB and has 0 slope until the corner frequency omega n, and after the corner frequency it has a slope of minus 40 dB per decade. And that's it. But the exact magnitude, as it was mentioned in the textbook, has a significant peaking around the corner frequency. Something like that. Let's try to find the exact peak location. First we need to do is to write the magnitude equation. Second, we have to take a derivative with respect to frequency and make it 0. Then, solving for omega, we will find the frequency where the peaking occurs, and substituting it back to the magnitude equation, we will find the value of this peak. Let's write the magnitude equation. Taking its derivative, in denominator we have a cube root, and in numerator we have a derivative of this argument. To have a 0, the numerator must be 0. Let's rewrite it. Simplifying this equation we have, then we can write that the frequency where peak occurs is omega natural times square root of 1 minus 2 zeta squared. Analyzing this equation, we can see that the peak exists only when zeta is less than 1/square root of 2, or approximately 0.7 0.0071. And the value of this peak can be found by substituting the equation we found into the magnitude equation. In the result of this substitution, we will find that the magnitude at this frequency is 1 over 2 zeta square root of 1 minus zeta squared. Let's summarize. Our derivations show that the peak at the quadratic pole does not exist when zeta, or damping ratio, is between 0.7 and 1. When zeta is less than 0.7, peak does exist, and it can be found by these two formulas. And if zeta is very small, the magnitude of the peak can be roughly estimated as 1 over 2 zeta, as the textbook says. The analysis is pretty straightforward, and I believe you can do it for quadratic zero all by yourself. Find the exact peak location and leave them in the comment below. If you like this video, hit the like button, share it with your friends, and subscribe to my channel. It was Misha. Thanks for being in the class today. Bye.